Good morning. Hope everybody's doing well. Hope you had a good weekend. Just a couple quick announcements. We are going through chapter 10 this week. Your test is going to be on Sunday. So your second test will be Sunday. You'll find it on Moodle, just like last time. Well, rather, it starts Sunday. You have Sunday through Monday. Do not forget to take it, please. I will remind you guys again on Monday. Make sure you take your test. What else? Thursday, October 15th, early voting starts in North Carolina. Woo! So if you don't know where your voting place is, make it happen. If you haven't registered to vote yet, you can still register. I believe you can register at the same time that you early vote. It's different for every state. So I'll have to take a look and let you guys know exactly on that. But get your vote in early. There are a couple different ways that people are voting this year. One is in person on the day of. If that's your thing, go for it. But I would go for early voting over day of voting, only because there is this global pandemic going on. And it could be really long lines and it could be really difficult to get in. And, if you go there and it's raining and you got to wait outside social distancing for 3 hours, maybe some of you will stay and vote, maybe some of you won't. So I would go early voting. There's another way too. You can also absentee ballot. If you are absentee balloting, you have to have that requested. I, again, would probably recommend voting in person, just because absentee ballots seem to be a point of contention in this election. So maybe get there in person and vote. If you are doing an absentee ballot, get it in as soon as you can, because we don't want to strain the postal system on the day of. And North Carolina is one of the few states, well, there's a couple states, but it's one of the states that will, if they open absentee ballots, they open them as soon as they get them, and they lay them flat so that they're all ready to glide through, so they can get those counted quickly. So the sooner we get them to them, the sooner they can get those prepped to count. Okay, that's all I'm going to say about that. So yay. All right, so we're going to work on chemical bonding. Chapter 10. This is sort of a visual chapter, so we're going to do some drawing. So you want to have some paper out, definitely, and a writing utensil. Okay, so I'm going to share screen here. Great. Minimize you guys over there. All right. So in 1989, researchers discovered the structure of the HIV protein, HIV being the virus that causes AIDS. So they were able to use bonding theories. So if you see this model here, this ball and stick model, this was something that they were able to put together in order to figure out the structure of the HIV molecule. It's important to understand the structure, because then you can understand its chemical properties. You can lead to therapeutics for that. So, there we go. So bonding theories are a set of ideas, concepts, drawings, sort of all these things put together that help us predict how an atom is going to come together, or how atoms will come together as a compound. So if I have oxygen and carbon, there's somewhat of a predictable way on how those are going to come together. They will help us determine what combinations of atoms will form and which combinations of atoms will not form. We can use bonding theories to predict why a salt is NaCl and not NaCl2. You've probably already got an idea of this from electron configurations, but we're going to show it visually using these bonding theories. And we'll also talk about why water is H2O and not H3O, what properties of water need this H2O. They also help us to explain the shape of these molecules. So you guys are going to start to understand what these molecules look like in 3 dimensions. We are going to draw them on paper flat first, and those are through Lewis dot structures. And then we're going to work on sort of stretching that 2-dimensional structure out into 3 dimensions. See what it looks like. So in bonding theories, the first thing we're going to talk about is Lewis theory, and then we'll talk about VESPR theory. So Lewis theory was named after a dude named Lewis. He was a chemist. And what he did was he would represent electrons as these little dots and draw them around the symbol of the atom, and he would call that a dot structure. So when we were working on the nomenclature lab, there was a part that had asked you about dot structures, and I said, just skip over that. We're going to be talking about that now. So these models that he came up with have tremendous predictability power. Great. We can determine which configurations will be stable and what a molecule might look like. So these are really great theories. These bonding theories are pretty effective. But again, just like everything, it's just a theory. We wouldn't actually know what it looks like unless we were to see the model firsthand, like with a mass spec microscope or something like that. And there are better models than the Lewis theory, but it has enough predictability power for us to use it for this class. You can make some pretty quick predictions using it. So when we're making these Lewis structures or these dot structures, we're going to take whatever the number of valence electrons are, and we're going to put it around the outside of the symbol. Now remember that you can calculate valence electrons by drawing the electron configuration, but that's a total pain. I would just go with looking at your periodic chart and remembering if you're in column 1, you have a +1 charge, or rather ditch that. If you're in column 1, you have 1 valence electron. If you're in column 2, 2 valence electrons. If you go all the way over to column 7, 7 valence electrons. So here is the electron configuration for oxygen. They drew the actual configuration out, and you see that you've got 2 and 4 in the outermost onion layer. But we know oxygen is in column 6, so we can just say it has 6 valence electrons. So how do we draw it as a dot structure? Well, we'll write the symbol for oxygen, and then we're going to draw the dots all around it, specifically 6 dots. Now, when you're filling in dots, you always want to fill them in singularly first and then go back and double up. So we would draw the symbol for oxygen. We consider there to be 4 quadrants or 4 sides. So 1, 2, 3, and 4. And so I'm going to put an electron here, and then one here, here, and here. And then I go back and double up. Now, would I actually know that while you're working on it, you filled them in singularly? No, not if you got to the right answer at the very end. But what I want to avoid you doing is this, where you go and you start doubling up right away. Because what you get is 2, or rather 3 complete pairs, and then 1 open side. This is a lopsided Lewis dot structure. This is not what we expect to see. So instead, we like everything to be singularly filled first and then go back and double up. All right, each dot represents 1 of the valence electrons. Great. A maximum of 2 dots per side. There's 4 sides. Fill in singularly first. It is important when you're working on the homework that you fill the dots in singularly. It will not like it if you double them up. All right, here's the Lewis dot structure for all the elements that are in the second period. Lithium is in column 1, so it has 1 valence electron. Nitrogen is in column 5, so it has 5 valence electrons. Look at what's happening with neon over here. Neon in column 8, it has 8 valence electrons. Everything's full. It's nice and happy. This is known as an octet. All right. Everything wants to be an octet. Everything wants to get to this sort of nice full configuration. Very stable. All right, so if we were to do the Lewis dot structure, say for phosphorus, phosphorus sits underneath nitrogen on your periodic chart. So it has more electrons than nitrogen, but it has the same Lewis structure as nitrogen because it's in the same column. And we only talk about valence electrons when we're drawing our Lewis structures or when we're doing our Lewis dot structures. So phosphorus has a total of 15 protons. So we're going to say it has 15 electrons. So this atom would have a total of 15 electrons, but when doing Lewis structures, only include the outer electrons. All right, I don't want to see 15 electrons stuck around here. When we look at helium, helium is an exception. Helium is one where you're going to put 2 electrons on the same side. So we're not going to fill it in. Let me draw it out. We're not going to fill it in like this. Helium and do 1 here and then 1 here. Why? Because helium forms this very stable thing called a duet that happens with the teeny tiny atoms. It's when their S configuration, their 1s configuration is full. Hydrogen will also like to form a duet, so I'm going to erase this because this is wrong. We don't want them singularly. We want to fill helium, hydrogen, double them up right away. So I'm going to go boop, boop, double up. Another one that likes to do that, hydrogen, if I was to have access to 2 electrons, we would give that a double up there. We wouldn't pack 8 electrons around hydrogen. We wouldn't pack 8 electrons around helium. Way too many electrons for those teeny tiny guys. So everything's going to want to become an octet on the periodic chart, except for the smaller guys. They are going to be fine with a duet. So pretty much for you guys, it's going to be hydrogen and helium. So in the Lewis theory, when we're dealing with chemical bonding, this involves a sharing or a transferring of electrons to give us a stable configuration. So everything wants to become an octet. So they're going to share or they're going to transfer. The same concept applies to previous chapters. If we're going to transfer electrons, we say it's an ionic bond. If we're going to share electrons, it's a covalent or molecular bond. Ionic, don't get freaked out. This is metal and a non-metal. Okay, hopefully that's been hammered into your brain enough times. Covalent or molecular is 2 non-metal. Non-metal, non-metal. Okay. Sharing, here we're transferring. So as far as a Lewis structure is concerned, a stable configuration will have 8 electrons, or it will follow the octet rule. We're going to transfer electrons or share electrons to get to 8. Now the octet rule applies to all the main group elements except for hydrogen, lithium, and beryllium. Those guys are cool with a duet. Most of what you're going to be working with is going to be hydrogen, is just remembering hydrogen wants the duet. So we'll go over this part a little bit quicker because we don't use Lewis structures a whole lot for ionic compounds because we can just sort of flip-flop to figure it out. But when we're dealing with a Lewis structure with an ionic, that means that it's a metal with a non-metal. The metal will give up an electron to form a cation. The non-metal will take on an electron to form an anion, and then the attraction between the two will stick them together. So let's look at this thing here. We've got potassium and chlorine. So potassium, if I was to draw its Lewis structure, I would draw it like this. Potassium with 1 dot. Why? Because it's in column 1, so it has 1 valence electron. Chlorine is in column 7. So we would put 7 valence electrons. You can probably start to see already that like this is not close to an octet. Well, it is close. It's close to the previous octet, right? The lower onion layer. But I'm not going to pack 7 electrons in here. Instead, if I was to ditch this, we would have a complete set from the previous. This guy is super close to an octet if he was just to take an electron on. So that's what is happening here. The electron is moving over. Now this will write as a plus, K plus. It doesn't have electrons around it because what we're assuming is that we have the complete set from the previous onion layer, right? We've got that complete onion layer of, where are we, potassium? Look what's going on before you, argon, okay? We've got the octet of argon. And now chlorine has taken an electron on, you'll put it in brackets, and it has negative charge. This gives us that idea of that predictability power. Why does this lose an electron? Why does this gain an electron? Well, because it gives it that octet. Looking over here at MgO. So magnesium has 2 electrons to give out. Oxygen has 6 electrons. Well, if the magnesium was to transfer, so take this electron and bring it over here, take this electron and bring it over here, what happens now is this forms a 2 plus charge because it's given 2 electrons up. This forms a 2 minus charge because it's packed 2 electrons. Does this have an octet here? Yes. Does this have an octet here? Yes, it does. It has an octet from the previous set, so stable. It's a lot of drawing of dots and it's a lot of work for just being able to flip-flop the charges, right? Let's look at one more here. So we've got sodium and so is there any big difference between sharing and transferring? Oh yeah. So when we're transferring electrons, this electron, when I transfer this over here, it's no longer being used by sodium in any way. Sodium has given it up to sulfur. In this case here, and it'll make a little bit more sense when we start doing the Lewis dot structures for 2 nonmetals when we share. So they both have access to the electrons. This guy doesn't want this electron, so he just throws it away, right? But if we look at sulfur, sulfur has 1, 2, 3, 4, 5, and 6. So if one sodium gives an electron, then it'll have 7 electrons. Is it stable? Not yet. So what happens is another sodium will give another electron. So we actually have 2 sodiums, each giving an electron to stabilize it out. So that's one way to come up with the structure, or you can always do the Na plus S2 minus flip-flop Na2S. This is a little bit faster than drawing this all up. Hold on one second. You want to go outside for? So yeah, transferring no longer, this thing doesn't have any of that access to electron. This guy has all of it. So let's look at when we share electrons. This is where we're going to spend a little bit more time, okay? So a covalent Lewis structure is where we have electrons that are shared. This is when we have 2 nonmetals that are, 2 or more nonmetals that are bonding together into a molecular compound, molecular, covalent, sort of interchangeable. Molecular compounds have covalent bonds where the electrons are shared much stronger. In Lewis theory, we will represent a covalent bond by allowing neighboring atoms to move closer together and share the electrons instead of transferring the electrons. We move them closer together and get them to share electrons so that everyone will have an octet, or for hydrogen, a duet. So let's look at water here, H2O. I'm going to draw this on a different page over here. Okay, so if I have hydrogen, hydrogen is column 1, so it has 1 valence electron. If I have oxygen, oxygen is in column 6, so it has 6 valence electrons. So this is a situation where I wouldn't transfer electrons. Why? Because if oxygen is obviously wanting some electron. Hydrogen is also wanting electrons. So if I just was to like erase this and then move it over here, well, oxygen's getting happy with its electron, but what happened to hydrogen? We just stole it from hydrogen. Hydrogen has nothing now. It doesn't have the complete set of the lower onion shell. It is the lowest onion shell, and it has nothing. It's unhappy there. So what we want to do then, instead of transferring electrons, is we want to think about sharing these electrons. So what if I took this hydrogen and just sort of moved him closer so that these electrons were in an area where they could overlap? That's what I'm going to do. So I'm going to put my hydrogen here. And that electron that was there, I'm going to put it right here in this range where it sort of is sharing. So in this case now, this hydrogen has access to these 2 electrons. What's going on with oxygen? How many does it have? 1, 2, 3, 4, 5, 6, 7. It's almost there. So why don't we put another hydrogen here and allow its electron to be shared as well? So what we have now is 2 hydrogens that are sharing, and the 1 oxygen that's also sharing. I'm overlapping so that we can see how these 4 electrons are actually benefiting both parties. Suzanne, does that make sense how they're sharing there as opposed to transferring? Okay, cool. So once you've drawn a structure, you want to make sure everybody's happy. So is hydrogen happy? Yeah, he's got access to 1, 2. This one has access to 1, 2. This oxygen has access to 2, 4, 6, and 8. Remember, everything wants 8 minus the hydrogen. And there is a system on how to draw this. So I will show you how to do that and how many electrons you even get to play around with. I'll show you that in a minute, but conceptually, I just wanted to show you how sharing is going to benefit much more than if I was to draw, let's say I had oxygen, we've got the 6 electrons, and then we've got hydrogen and hydrogen with 1 electron. Well, if he ditches his electron and he ditches his electron, oxygen, so happy. Both of these hydrogens, not happy at all. They're not getting anything. So that's not going to work for this situation. Okay. So they have a little bit of a better drawing than I can do. But what we can see is that these electrons are being shared here. The oxygen is receiving its octet and the hydrogen is getting the duet. Both are happy. They're not having to transfer. They're having to share to do it. So we want to be able to differentiate between different pairs of electrons. So the electrons that are being shared are known as bonding pairs. So these guys here and these guys here are known as a bonding pair of electrons. On the oxygen in the center, there's some electrons that aren't like involved in any sort of bonding. We need them there. We don't want to ignore them, but they are not attached to an adjacent atom. So we will call those lone pair of electrons. Now, the wording can be a little tricky. If I was to ask you, hey, how many bonding pairs are there? It would be 1, 2. If I was to ask you, hey, how many bonding electrons are there? It would be 1, 2, 3, 4. Same thing with lone pairs. If I was to say how many lone pairs of electrons are there, it would be 2. If I was to say how many lone electrons are there, it would be 4. So just make sure that you're looking at, are they talking about it as a pair? Or are they talking about it individually as an electron? Now, to clean these structures up, those bonding pairs, a lot of times we'll draw as a dash, okay? So when you see this dash down here, everything is in my way. Come on, dude. Go somewhere else. When we look at this structure here, this line is representing 2 electrons. That just helps your eye to differentiate between bonding things and non-bonding things. We'd never draw a line for lone pairs. Those will always be dotted. All right, bonding will get the line. So when looking at this right away, I can see real easy, oh, there are 2 bonding pairs and there's 2 lone pairs. Chlorine. So chlorine is one of those things that we said was a diatomic molecule, right? Why is it a diatomic molecule? Why does it like to stick to itself? Well, look at the configuration of chlorine here. There are 7 electrons, so close to an octet. So what it does is it comes together with a buddy. This chlorine has 7 electrons. This chlorine has 7 electrons. And when they share those 2 guys that are unpaired, they each get access to an octet. So now they're stable and happy. We would draw it like this, right, with the line between. Hydrogen, again, is another one of our diatomics. Hydrogen has 1 valence electron. It wants a duet. So why doesn't it just pair up with another buddy? And then look at that, they can share 2 electrons and they both have access. We draw it like this. Oxygen is one of those things, I'm going to draw this on another one, that likes to form a duet. So if we have oxygen by itself, oxygen 1, 2, 3, 4, 5, and 6. So we know it likes to form a duet. Can you just add another element if it doesn't have enough electrons? No. You have to honor however many electrons are in the given formula. Okay, so when we're doing Lewis dot structures, if I was to give you H2O, there better not be more than 2 hydrogens. Okay, if we want to satiate it. And I'll show you guys how to go through that step by step. So this guy here, we've got another oxygen. We know that this likes to form a duet. So I know that there's going to be 2 of them. So these 2 electrons that are unpaired are going to become a shared bond. So this oxygen now has access to 2, 4, 6, 7. It's getting closer. So what ends up happening is that this electron will actually bond with this electron, and we get what's known as a double bond, like this. Okay, so there are 4 electrons bonding right now. If we look, this oxygen has access to 2, 4, 6, 8. This oxygen also has access to 2, 4, 6, 8. I will teach you guys when to use double bonds and things like that. So there's our oxygen. We've got a double bond. Nitrogen, also a diatomic. It forms a triple bond. So each one brings 5 valence electrons. So we have not just 1 or 2, but we actually have a 3 or a triple bond. So the structure would look something like this. Each nitrogen would have 1 lone pair, and then there would be 3 bonds in the center. Triple bonds are stronger than double bonds. Double bonds are stronger than single bonds. You're never going to have a like tetral bond or 4. 3 is the max. So it's either going to be a single, double, or a triple bond. Looking at this nitrogen over here, I'm going to circle 1 nitrogen with the bond. I'm going to circle the other nitrogen with the bond just to double check that everybody's happy. 1, 2, 3, 4, 5, 6, 7, 8. This guy is good. This one over here, 1, 2, 3, 4, 5, 6, 7, 8. This guy is good. So in these covalent bonds, it is beneficial for each thing to share the electron as opposed to transferring. If they transferred, one guy wouldn't be happy. So just know double bonds are shorter and stronger than single bonds, and triple bonds are shorter and stronger than double bonds. Okay, so how do we write these things? So this is the way you're going to go about it. First, you'll be given a formula. Okay, so I'll give you something like, and we'll just do water because we already have sort of looked at its structure. So I'll give you a formula. I'll say, hey, write the Lewis-Dach structure for H2O. What you want to do is write the correct skeletal structure for the molecule. When I say skeletal structure, I mean put the atoms in a certain way so that the molecule looks balanced and the atoms are in like a relatively balanced position. There are certain things that like to be what are known as terminal atoms, or those are atoms that are at the end. Hydrogen is one of those. Hydrogen likes to be on the outside. Why don't we put hydrogen on the inside? Because hydrogen only wants 2 electrons. It likes a duet. If you stick it in the middle, it's going to end up getting packed with more than 2 electrons. It's not going to be happy. Oxygen tends to be a central atom. It likes to sit in the middle. Is it always a central atom? No, but carbon is most of the time a central atom. Anything that can have 8 electrons is a potential to be a central atom. The only way to absolutely know the correct structure, again, is to examine it in nature, but you know, we can get pretty good at this. Now, so we're looking at water right now. Couple rules when drawing the skeletal structure. Hydrogen will be a terminal. Hydrogen likes a duet. Most molecules are symmetrical. So you'll have several types of the same atom on the outside. Are there exceptions? Of course, there's always exceptions to all these rules. But when looking at water, going back over here. So if I give you the formula H2O and I say draw a Lewis-Dach structure, what does it look like? I'm going to put the oxygen in the center and I'm going to put the hydrogens on the outside. Why? Hydrogens like to be terminal. Oxygen is cool being the center atom. Also, this looks relatively balanced. I would never want to draw a structure like this, H, H, O. One reason, it's not balanced. Another thing, this doesn't like to be in the center. Okay, so this is all wrong. So first step, getting it to look sort of like this. Next step, and sometimes step 1 and step 2 get flip-flopped. It's okay, you can do step 2 first. I tend to do step 2 first, but calculate the total number of valence electrons for the Lewis-Dach structure by summing up the valence electrons of each molecule. So we've got to figure out how many electrons do I even get to put on the board? You know, where does that come from? Am I just guessing? No, you will use however many valence electrons each one gives you. So hydrogen is in which column? Column 1. So it provides 1 valence electron. But how many hydrogens are there? In this case, there are 2. So we're going to multiply this by 2. And we're going to add it to the number of valence electrons that oxygen gives us. Oxygen is in column 6. So it gives us 6 valence electrons. How many of them do we have? Just 1. So we have a total of 8 electrons. So when you've calculated this number, this is how many electrons better be on the board. You cannot have more than 8. You cannot have less than 8. That is going to restrict how your structure looks. We never want to go, oh, well, I need more electrons, so I'm just going to add 2 here. Don't do that. You'll use a different system. All right. So we've got a skeletal structure, check. We've got our valence electrons, check. Let's see what the slides tell us. Oh, this is important. If you are dealing with a polyatomic ion, you do need to take into account the charge of the polyatomic ion. And I will tell you guys about that. So if like we had sulfur, let's go sulfate. I'm gonna draw a sulfate over here. So a sulfate is SO4 2 minus. If I was to draw its structure, I'd put sulfur in the center and 4 oxygens around the outside. That seems symmetrical to me. And then when counting the valence electrons, sulfur is in column 6, so it has 6 valence electrons, plus oxygen has 6 valence electrons times 4. Okay. We have to take this into account. And this, people always get this messed up, but if it has a negative charge, that means we're adding 2 electrons. If it has a negative charge, we're adding 2 electrons, because what is a negative charge telling us? We have 2 additional electrons. People will see this and say, oh, I'm going to subtract 2 electrons. No, you want to add 2 electrons. So in this case, we'll have 6 plus 6 times 4 plus 2, which will equal 32 electrons to play around with on the board. A lot more electrons here than here. So add 1 electron for each negative charge, subtract 1 electron for each positive charge. All right, distribute the electrons among the atoms, giving octets and duets whenever possible. All right, I will teach you how I like to do it. So the way that I do this, I have 8 electrons to play around with. I am going to bond the thing together first. If it's a compound, I know that they have to be bonded. So I'm going to put a single bond here and here. I'm going to stick it together. That's the first thing you do, is make your bonds. How many electrons do we have on the board currently? 1, 2, 3, 4. 4 electrons. Now you always want to follow this rule of thumb. Make the outer guys happy first, and then work to make the inner guy happy. Don't work from the inside out, work from the outside in. This one doesn't matter so much, but it will at certain points. So I'm going to go to my hydrogen. Is my hydrogen currently happy? Yeah, he's got access to 2 electrons in this bond. So this hydrogen is good. What about this hydrogen? He's good. All right, who do we want to go to now? We go to the center guy. Is this oxygen happy? Currently, it's not happy, right? He has access to only 4 electrons, but few, we've got 4 more electrons to play around with. So I'm going to put a bond here, or I'm sorry, not a bond. I'm going to put a lone pair here and a lone pair here. How many electrons are on the board? 1, 2, 3, 4, 5, 6, 7, 8. You always want to be checking to make sure you have the right number of electrons. Hydrogens are happy. Is oxygen happy? 1, 2, 3, 4, 5, 6, 7, 8. Yes, they're all happy. Okay. Now, if you put your dots in a different position, you may have put your dots like here. 1, 2, 3, 4. That is fine. It's a 3-dimensional structure. So I'm, as a teacher, I'm looking at this like I'm kind of moving it around in space. Pretty much. Hydrogen and helium, yeah, are going to be the only guys that are good with a duet. Sometimes you'll see beryllium, but yeah, you're going to be good with just hydrogen and helium. So dots are fine there. What I don't want to see is this, though. You're not going to put 1, 2, 3 dots and then 1 on the bottom, because they're always going to be a pair, paired together. We don't like that. But let's say you're drawing, you're like, well, I put my dots on the bottom. Great, that's fine, as long as these are coupled together. So you make sure everybody's happy, and you've made the correct Lewis dot structure for it. Let's go over here to sulfate. Sulfate has a lot more electrons. So I'm going to first thing bond. And if you're thinking, do they really count all those electrons? Do the teachers really? Yes, we do. So make sure you're putting them correctly in there. All right, so we're going to bond it together first. I'm going to bond that. 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 Now I'm going to make the outer guys happy. So this oxygen here has access to 2 electrons. How many does he want? Everything wants 8, minus hydrogen and helium. So I'm going to give him 6 more electrons. 1, 2, 3, 4, 5, 6. This guy also needs to have an additional 6 electrons. Same thing with this one. And this one. All right, how many electrons are on the board? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. 32 electrons on the board. Can't add any more electrons, can't take any more away. Is everybody happy? Well, I know the oxygens are happy because I just filled them to be happy. Is sulfur happy? Yeah, sulfur is actually happy. 2, 4, 6, and 8. So everybody is set and the structure is done, almost done. The last thing I want to do, because this is a polyatomic ion, is just put it in brackets like this and put a charge on the outside. Just to let the reader know I'm not dealing, because if you didn't have the brackets, then I'm going to look at this and say, hey, where did you get those 2 extra electrons? You should not have 2 extra electrons like that. Well, now you're telling the reader you can't have 2 extra electrons. All right, if there's one more step here, if any atoms lack an octet, form a double or a triple bond so that we can get to that. So let's do one that lacks an octet once we've got all the electrons on the board. So we've got CO2. All right, I'm going to calculate my valence electrons first. I don't know why, I just like to do that first. So carbon gives us 5 electrons because it's in column 5. No, wrong, totally wrong. Carbon gives us 4 electrons. It's like, that's not going to work out for us. Carbon gives us 4 electrons because it's in column 4. Oxygen gives us 6 electrons and we have 2 of them. So 12 plus the 4 is going to be 16 electrons. Make sure there isn't 14 electrons, make sure there isn't 18, we want 16. So now I'm going to draw a structure on this thing that is relatively symmetrical. So carbon I'm going to put in the center and the oxygens I'm going to put on the sides. Why didn't I put oxygen in the center here? Because then I have to put carbon on one side and oxygen on the other side. That doesn't look very symmetrical. So I want to keep them balanced. Okay, so after you've got your skeletal structure, you want to stick it together. So I'm going to put a bond here. I'm going to put a bond here. So I've used up currently 4 electrons. I need to use 16. This is an example where you don't want to make the inner guy happy first. If you start working the inner guy first, it's going to mess you up. So do the outer guys first and then work towards the inner guys. So this oxygen has access to 2 electrons here. So I'm going to give him 6 more electrons. This guy over here has access to 2, so I'm going to give him 6. How many electrons are on the board? 2, 4, 6, 8, 10, 12, 14, 16. Okay, I've used all of my electrons. You only make double bonds or triple bonds when you've put every single electron on the board. Don't double bond and still have electrons in your bank. So sometimes students will stop here and say, I'm done, because I used all my electrons. Well, you're close, but this oxygen is happy. This oxygen is happy. What about carbon? Carbon currently is not happy. He only has access to 1, 2, 3, 4 electrons. He wants to have access to 8 electrons. So can I put 2 more electrons? This is another fault that I see people. No, we can't do that. Why? You can only have 16 electrons. So what needs to happen is these oxygens need to get a little bit more generous, and they need to move a pair into a double bond position. So this oxygen over here is going to say, hey, you know what? I'll share with you. This oxygen over here is going to say, I don't know why it won't erase my circle, but it won't. I'll share with you over here. So now we always, whenever you're making double and triple bonds, I'd always check to make sure that you haven't like left some electrons lying around. So I recount. So 2, 4, 6, 8, 10, 12, 14, 16. I still have 16 electrons. Is oxygen happy? Yes. 2, 4, 6, 8. Is this oxygen happy? Yes. 2, 4, 6, 8. Is carbon happy? Yes. 2, 4, 6, and 8. So this is a situation where we've had to make a double bond in order to satiate one of the guys. Don't ever do it though if you haven't used all your electrons. You'll get into trouble. Let's see. Okay, so let's do one for a polyatomic ion. Let's just throw it out there. I'm just gonna have you try and do it and see if you can do it, okay? So we're gonna do for cyanide. Cyanide is CN with a minus charge. So you should be able to draw a skeletal structure and you should be able to calculate valence electrons. I want you to do that at a minimum and then try and distribute the electrons if you can. Making double bonds or triple bonds, hit where you need to. Okay, so carbon gives us 4. Nitrogen gives us 5. If you were to stop there, you would have ended up with 9 electrons. Ooh, we don't like odd numbers. Does it happen? I mean, yes, in some of your higher up chemistries, you'll have odd numbers. For the sake of this class, we're gonna keep it simple. You better have an even number of electrons. So if you're not having that, you probably are dealing with a polyatomic ion, you need to adjust your charge. So what does the negative charge say? It says add an electron. For every negative, add. For every positive, subtract. So we should have had 10 electrons. If you ended up with 8 electrons, it's going to give you a different structure. So you got to be able to calculate that. It's only 2 atoms, so you could do carbon, and nitrogen, or some of you guys might have gotten really crazy and put nitrogen and carbon. It doesn't matter, all right? Why? Because the structure is happening in 3 dimensions. I could just flip it. So the first thing I want to do is stick it together. Bam. Now I'm going to make the outer guy happy. Okay, there's not really a definitive outer guy, so we're just going to pick one. So 1, 2, 3, 4, 5, 6, 7, 8. I've got 2 more electrons, 9, 10. If you had filled carbon in first and gone to nitrogen after, that's fine as well. Right? So in my structure, which may be mirrored of your structure, my nitrogen is happy. My carbon isn't happy. Your carbon may have been happy and nitrogen not. Either way, what do we got to do? Nitrogen needs to learn to share. So that has to move over here. Okay, so I moved one over. Carbon is getting closer to being happy, but it's not quite there yet. So nitrogen has to be even more generous and bring another one of those electrons over here. Recount and make sure you have 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons still on the board. Is carbon happy? Right now, carbon is happy. Is nitrogen happy? Now nitrogen is happy. Yes. 2, 4, 6, 8. 2, 4, 6, 8. If your little dots were on the top or on the side or whatever, that's fine. Just make sure they're paired together. Where did I get the 5 from for nitrogen? The 5 came because nitrogen is in column 5. Okay, so for the main group elements, column 1 with hydrogens and all them is 1. Carbon is in column 4, so we gave it 4. Nitrogen is in column 5, so I gave it 5. So I'm not pulling those numbers out of thin air. Would there be? Yes, there would. There would totally be brackets. Okay, so let me make this look a little bit neater. Yes, bracket, bracket, minus charge. So this is the system you always want to follow when you're doing Lewis dot structures. You always count the valence electrons, make a skeletal structure, bond it, make the outer guys happy, then work to make the inner guys happy by making double and triple bonds if need be. Are there exceptions to the octet rule? Obviously, there are. There are things that like less than. Boron is like really happy with 6. There are things that like more, like sulfur, like what these things that are called expanded octets. 12, phosphorus can have 10. Am I going to test you on exceptions? No. In 151, you do get tested on exceptions if you're going to take that. But for this class, no. So you can just leave the exceptions. I'm not going to talk about resonance structures yet. We're going to do a couple of these from our lab book. So grab your lab manual out and let's just kill 2 birds with 1 stone. I'm acting all confident like I have my lab manual. Come on, Candace. You got it somewhere in here, don't you? Okay, good. Phew. No, I don't. I pretty much have this lab memorized though. So Suzanne, because I can see your face. You have your lab manual. Can you give me, there's on the first page, there are like of the drawing section, there are examples, right? Isn't there like water? Or there's, what is it? Yeah, we've got, yeah, okay, so I want you to skip those first 2 because they're exceptions. We'll do CF4 together. We've already done H2O like twice, so you can do H2 on your own. We'll do CF4 and we're going to do SiH4 together, okay? Perfect. All right, great. So let's start by doing, I want you to do CF4. Now, everybody's lab is a little bit different on how, depending on what, some people have older labs, so they don't ask the exact same thing. Don't stress too much about like where it says how many lone pairs, how many valence pairs. Let's see, what am I doing here? Spacing out. Okay, so CF4. So the question should, like at the very top, should ask you like how many valence electrons you have. Is that the first question? It's different for every lab. Yeah. Okay, so let's calculate the number of valence electrons that we have for this. So I'll give you all a minute to do that. Not even a minute, like 26 seconds, exactly. Okay, so fluorine is 7 times 4 is 28 plus 4, 32. 32 electrons. So yeah, let me draw it. It said something like valence electrons. So we have 32 of those. Then next to the lab, or next to the, like all the different writing, there should be like a little open section on the right. So that's where you're gonna draw your Lewis structure. I would recommend doing this lab in pencil because you're gonna have to be erasing dots and stuff. So I want you to draw the Lewis dot structure for CF4. Yes, Leanna, just skip BCl3 and BEH2. If you, the first two, if you want to skip, yeah, the example 1 and example 2, you can, if you want to go back and do it because you want to try it, but just letting you know those will be exceptions. Okay, so we have 32 electrons. Some of you guys, my smart cookies in here, may be thinking, ooh, 32 electrons. Didn't that sulfate have 32 electrons? It's a lot of electrons. It's going to have a very similar structure. So I'll put carbon in the center. Fluorines, got 4 of them on the side, kind of like the sulfate, right? The sulfur with the 4 oxygens. Bond, then make them happy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. 32 electrons on the board. Are the fluorines happy? Yes. Is the carbon happy? Yes. You're done. Okay. Well, you're not done because there's a couple other questions, but we haven't gotten to it yet. What's the next thing it says after valence electrons? It should ask you how many like lone pair domains you have, or lone pair domains. Okay. So when looking at lone pair domains, you're only looking at what's happening on the central atom. Domains around central atom. Okay. So how many domains do I have around this central atom in total? I have 1, 2, 3, 4. We will talk about this in depth a little bit more next time, but just so we can get through this one, we have 4 domains. How many of those are paired? All 4 of them. So your paired domains, number of bonding domains around central atom. Great, thank you, Susan. So that would be 4 for that guy because we have 4 areas. Number of, one of them should say, yeah, if you want to help me out, Suzanne, I don't know where my lab book went. So I'm looking in the chat right now. Okay, so number 3, number of non-bonding domains around central atom. So are there any of these domains here that are non-bonded? No, all of them are bonded pairs. So we're gonna say 0 for number 3. And then for number 4, ditch VESPR. Yeah, we're not gonna do that just yet. Just leave it as is. And then geometry, yeah, we'll leave all that for right now, okay? We'll come back to it. So let's do, I don't want to do water. I want to do that pH 3 one. So that should be number 2 on the actual lab, not the examples. So pH 3. It's called ammonia. So calculate valence electrons, draw a Lewis structure, and then see if you can come up with how many bonding domains there are and how many non-bonding domains there are. Yeah, Lyric, I will go over C4 real quick with you. Everybody else, you can just keep working on the pH 3. So Lyric, what we did was we had CF4. For valence electrons, we calculated a total of 32 electrons. There's 28 coming from the 4 fluorines and then 4 coming from the carbon. We drew the carbon in the center and the 4 fluorines on the outside to create a balanced structure, and we bonded them together. Then we filled in electrons around the outer guys first, the fluorines. So I added 6 to each of the fluorines to make those happy. That totaled 32 electrons. So then I just needed to check and make sure carbon was happy. And carbon in this case is actually already happy with just the single bonds. So we didn't have to make any double bonds and the structure is done. Number of bonding pairs. So how many pairs are involved in a bond? 4. How many bonds or how many pairs are involved in non-bonding? On the central atom, none. I know there's lone pairs around the outside here. We don't include those when we're looking at lone pairs for central atom. They don't affect the shape. Okay, so pH 4. Let's do this. You should have, okay, great. And Lyric, if you want, you can always go back and look over the slides or look over the videos on YouTube again if it's not clear. So we have 8 electrons to play around with. My structure, I'm going to put P in the center. I'm going to put my H's on the outside. Why am I putting the H's on the outside? 2 reasons. One, because H is a terminal atom, and also because that makes it look symmetrical. I'm going to stick them together. Bam, bam, bam. Now I am going to work to make the outer guys happy. Well, in this case, the hydrogens are already happy. We wouldn't stop here. How many electrons do I need on the board? I need 8 electrons. And who isn't happy? Phosphorus isn't happy. So what do? Well, let's just give them 2 electrons. And you're done. Okay. When the question said, how many bonding domains are there? 1, 2, 3 of them are bonding. How many lone domains are there? 1. Okay, 3 and then 1. That will affect its shape, and we'll talk about that next time. So that's how part of this lab is going to work. We will work on the VESPR other stuff next time, but I want to do one more Lewis dot structure. One more. And then that will cover, we will be good, hopefully, with Lewis dot structures. Okay, so SO2, yeah. So let's do SO2. I want you to try and do it on your own. There's going to be something a little funky with it, but give it a try. SO2. Might be able to figure it out. Okay, so figure out how many valence electrons it has and figure out how many and what its Lewis dot structure looks like. We're not going to do the one on the lab yet. Okay. Yeah, we'll come back to SO3 another time. We're going to do SO2 specifically because I want to teach you about something. Okay. All right, just so that we can have time to go over this thing. So SO2 minus, this would be if someone was to give this to you or I was to give it to you on a test and say sulfur dioxide, instead of writing it this way, you would be able to write that formula because nomenclature never goes away. So make sure you still got that around. How many electrons? Let's see, 18? 18 electrons to play around with. Sulfur is going to go in the center. Oxygen is going to go on the sides. I'm going to stick it together. And I'm going to make the outer guys happy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, 17, 18. So 18 electrons are on the board. Oxygen is happy. Both of the oxygens are happy. The sulfur is not happy. He has access to 6. He wants access to 8. So I need to make a double bond. Could I make it here? Sure. Instead, could I have made it off of this one? Sure. What I can't do is make it off of both at the same time. Why? Because then that would give me 2, 4, 6, 8, 10 for sulfur. We don't want that. But when you get into a situation where you can make a double bond, you need to make one. This is oxygen 1, this is oxygen 2. And it can go off of either one. That's known as a resonance structure. Resonance because it's the double bond. We can think of it as sort of resonating back and forth between these two. So I'm just going to put it on oxygen 1. You could put it off of your oxygen too. That's fine. Sometimes you'll see it written like this where you have a double bond, and then they'll do like a little dash, dash, dash to let you know that the double bond is sort of oscillating between the two. It's not really oscillating, but what ends up happening is you have this like 1.5 bond on both of those. So anytime you get to a situation where you could make a double bond here, or you could make a double bond here, but you can't make it on both, that's known as a resonance structure. I want you in your lab to denote anytime that you've got a resonance structure. Okay, the lab doesn't explicitly say that. So just underneath your Lewis structure, if you get to one where it's a resonance structure, just write like RS or something next to it. So could you have done a triple bond from both oxygens? I don't even know. Let's see. That sounds like there would be way too many electrons on the central atom. If you had a triple bond here and here, and then we were to get rid of this and this and this, 2, 4, 6, 8, 10, 12, 14, 16, 18. There are 18 electrons on the board, but whoa, what's going on with sulfur here? He's having like a party with these electrons. It's like super greedy, right? 2, 4, 6, 8, 10, 12, 14 electrons. How many does he want? 8. Are there exceptions to the rule? Yes, but this is not one of them. Does that make sense, Harley? Okay, cool. Totally common, happens. That happens, yeah. Okay, so that's a resonance structure. Just real quick before we finish, I just want to show it drawn here. So sometimes they'll draw each structure and put like an arrow between them to let you know that it's a resonance. The double bond is oscillating between the two. I'm fine with you just drawing one of them and just writing that it's a resonance structure underneath it. Okay. So that's a good stopping point because we're going to move into VESPR theory for next time, which will give us the shape of these. Great. Hopefully that was helpful. Let me know if you have any questions. Stay around. If you don't, leave and go figure out where your voting station is. And I will see you guys on Wednesday. Okay. Bye.